For the ADCS system, it's responsible for all the different actions in here. So let's dig into each one. When it comes to the sensing action, we want our ADCS subsystem to sense external cues from the environment. This could include Earth's limb, which is the horizon of Earth. It could include the direction of the sun, or maybe even the detection and direction of other celestial bodies, like the moon. Other useful measurements could include the magnetic field, if you're in low Earth orbit, or if you're maybe around Jupiter. You can also use the stars as reference cues. You can see here there are certain constellations that are labeled, and you can formalize. For us, when we're stargazing, we recognize constellations. For satellites, they pick up on these little dots and do some pattern recognition. Based off of the constellations that you see, you can figure out how you're pointed in Earth. Other subsystem responsibilities include, the next step, incorporating these sensor measurements into an attitude determination algorithm that resolves attitude. So you'll see here a kind of attitude determination technique where we use the magnetometer, so the magnetic field, and the sun sensor, which measures the sun direction. There are a lot of vectors here, but let's just look at the pink vector and the red vector. So the magnetic field is going to give you some bearing on how you're faced relative to where you are in the magnetic field. And then the sun direction, based off of your sun sensor, is going to give you another vector. So given these two vectors, you can hone in on how you're oriented in space, where this green coordinate axis is your attitude in inertia frame, and then the blue is in body frame. So given the orientation of these two coordinate frames, you can resolve how many degrees off am I from my body frame to the inertia frame, for example. There are many different sensors that you can use. We talked about that last time, but the different sensors come with different accuracies and different design considerations. A sensor I didn't talk about in the last slide is IMU, which is inertial measurement unit. And you can incorporate gyroscopes within to measure angular rate. So here we'll talk about this collection of sensors and the pros and cons of each sensor in a later subsection and lecture. The ADCS system, the C part, is controlling the spacecraft's attitude by sending control algorithm commands to actuators. So we'll go into different actuators later, but one of them is called a control moment gyroscope. So let's look at this test setup. We've got control moment gyroscopes, which are these wheels that carry angular momentum with them. Angular momentum is the way that a spacecraft is spinning or tumbling through space. And you can cleverly control the angular momentum of the system with little bodies, with little control moment gyroscopes embedded within the spacecraft. So imagine that this platform is the spacecraft itself, and it encapsulates these little rotors that are spinning at some high speed. So the ACS, while it was off, you saw that with a disturbance, the system would oscillate and then dampen out naturally based off of the friction of the system. But when you have the clever control, or ACS, on, then the spacecraft would oscillate and bring itself to an equilibrium much faster. Do you see that click in? So there are much less oscillations between when the disturbance happens and its steady state. So a control system takes in measurements, figures out how to compensate the system so that it either stabilizes or tracks a trajectory, something desired, and cleverly yeah, dampens out that kind of oscillation. Okay, so part of that control is, given the mission, how do we want to point, track, or slew along a trajectory with some level of precision and accuracy defined by the needs of the payload? So here we will see a mission where a spacecraft is trying to point at certain cities along the US. It's not the most inspired mission, but I just wanted to show you the slew maneuvers that this engineer created to track the different cities. So you can see the spacecraft is pointing nadir and is not only slewing along the vector of velocity, but also slewing, rolling or pitching side to side to track the different latitude of cities. Okay. So to achieve this subsystem, the subsystem lead needs to select sensors and actuators that ultimately yield the precision pointing or tracking accuracy and precision. We'll talk about, again, the pros and cons of different sensors later, but the ones to select from are IMUs, star sensors, sun sensors, earth sensors, which are like the horizon or the limb sensors, and magnetometers. The subsystem lead is responsible for conducting analysis on the external and internal forces and torques to discover contribution to spacecraft dynamics due to these disturbances. So in a previous slide, we saw the control moment gyroscope test setup where a hand was imparting external disturbances onto the system. You can imagine that that hand could be it could be vibrations from components inside, like if there were a cryo cooler inside of the spacecraft. It could be the atmospheric drag that is imparted on the spacecraft if the spacecraft is in low Earth orbit. It could also be magnetic field disturbances if you have some kind of magnetic field within your spacecraft, like a bar magnet or your really strong electronics. Or if you have even magnetic motors within your spacecraft, you'll have to maybe compensate for the way that the magnets on the inside interact with the magnetic field on the outside. So regardless, you'll see that the loop for understanding, for conducting analysis include, if you want a certain attitude, you determine your attitude, you determine your control, and at some point in the loop, you have to compensate for environmental disturbances. So these environmental disturbances, they're not known. They are measured or estimated to a degree. So if they're not known and you have to measure them, then your spacecraft needs to react, which means it measures and then acts post-measurement. If you do know your environmental disturbances, then you can proactively reject those disturbances. So you are adding control before you experience the disturbance itself. So what can these environmental disturbances be? We talked about the magnetic field, atmospheric drag. Here, there are micro vibrations that could happen from your structures. There could be your actuators generating different vibrations like harmonics or broadband wheel disturbances. If the wheel, for example, is imbalanced, then while the rotor is spinning on the bearing, it can wobble, and that could create disturbances as well. And I thought this was just a neat picture depicting the different frequencies at which these dynamics are imparted. If you have a flexible appendage on your spacecraft, the flexible dynamics of, let's say, an articulated arm or a solar panel that's extended out, that could also be a part of your disturbances that you want to reject. To conduct analysis, you may want to test your system out in some kind of attitude determination control simulator, which is shown here. Here is a Helmholtz cage, which simulates magnetic fields. There's an air bearing in the middle that simulates frictionless motion in 3 degrees of freedom. And then you want to simulate a bunch of space environment effects. So the sun, the magnetic fields, frictionless motion, and maybe some sensors as well, like GPS. Another subsystem lead responsibility is to coordinate with the structures and mechanisms lead to place and mount sensors and actuators with unique requirements. So for example, there are cameras that would want unoccluded field of views to the space environment. This could be star trackers that want to see the stars, of course, sun sensors. We have GPS antennas that also want to be on the outside and unoccluded. There are some things that want to be oriented in certain ways. You'll see here the reaction wheels are systematically configured to position their angular momentum vector, or pretty much the spin axis of the rotor, in linearly independent ways. Linearly independent, kind of in math speak, but converted to physically, you just want to make sure that there's some component. Okay, I'm going to go with math speak. Some component of this plane that is pointed in unique directions. That way, you can control the spacecraft in unique ways. There are just some other common things that you want of your sensors when you're mounting them. You just want to make sure that the axes that you mount them with respect to are orthogonal to the spacecraft. So you'll see like corners are lined up with other corners of the spacecraft, etc. So let's see. Yes, to place and mount sensors and actuators. Assumption of this subsystem responsibility is just choosing which sensors and actuators. So here, this subsystem chooses sun sensors, 2 of them, magnetometers, gyro, 2 star trackers, a GPS. And for actuators, they pick magnetorquers and reaction wheels. Speaking of magnetorquers, these magnetorquers are facing 3 distinct directions. So maybe that's a way to physically describe linearly independent. You'll see this one is aligned with Z, this magnetorquer is aligned with X, and this magnetorquer is aligned with Y. Another subsystem lead responsibility is to calculate and code algorithms to estimate position and attitude states. You also want to control the spacecraft attitude to the required accuracy and precision. You may need to develop a simulation environment to verify that this is true. Here we have a block diagram of different ADCS algorithms and the interaction or flow between them. So from ground, you can come up with commands. The orange is more so a mission operations and CDH, command and data handling thing, but the blue algorithms are all within the scope of attitude determination control. So let's see, some inputs could be all of your sensor measurements. So your role now is to process those sensor measurements determine attitude. Before we go into these more integrated algorithms, let's go into the other isolated algorithms. You could also take in commands for your navigation and guidance and momentum management, which can generate a specific command. You're converting maybe a human readable command to something that is more interpretable for the hardware. For attitude, determination, and control, navigation in particular, it's very important to get time. And then you can also get a GPS. You can get a GPS position measurement for your navigation algorithm. GPS also gives time. Your navigation algorithm needs ephemeris, which are pretty much the positions of different celestial bodies. It's like the position of the solar system at different snapshots of time. Anyway, you're managing all this information to eventually control your thrusters, to generate controls for your reaction wheels that eventually get passed along to your hardware. So this is where you take absolute commands for how you want to control your reaction wheels, and then there's some translation to send that command to the hardware itself, so hardware interface.